Hi, in this video we're going to go over the solutions to Worksheet 7.4. So let's see here. Let's start things off. So the main idea of this worksheet is to um, basically practice taking the energy bar graphs and writing equations for those. So that's kind of the big idea here. As we start off, number one here, the first thing you kind of want to do is take a look at each situation, try to figure out what kinds of energy are going on. So as we look at the first one, this little cart appears to be moving, so that means it's going to have kinetic energy. It is not up high, so no gravitational energy. And at the initial situation, there is no elastic energy either. Take a look at the final situation. It does not appear to be moving, so that would mean no kinetic energy. It does not appear to be up high, so no gravitational energy. There does appear to be a spring, so that would give it elastic energy. And again, we're not utilizing the internal energy bit. Next step is to try to figure out what you should probably include in your system. So there's kind of two objects that you might choose to include here. The first one would be the cart. So probably put that in there. Second one would be the spring. Those are kind of the two objects involved in this situation. And so I'm going to start us off with 4 bars of kinetic energy. 4 is a nice number, just allows you to split it up later if you needed to. Since there's no work done because there's nothing adding energy between the initial and final, and there's also no friction or anything that's causing us to lose energy between the initial and the final, and so no work done there. That would mean that basically we just end up with some elastic energy at the end. So to write the equation, recall that the equal sign pretty much lives right there. So that's just going to give us EK. All right, plus 0 to remind myself that the work is 0, so I don't kind of forget that step, is equal to the elastic energy. And kinetic energy is 1/2 mv squared, and elastic energy is 1/2 kx squared. So that's going to give me 1/2 8 5 squared equal to 1/2 50 x squared. And I am solving for how much is the spring compressed. So that means I'm solving for the x here. So let's do this. We got 1/2 times by 8 times by, that's going to be 4 times by 25, which is going to give you 100 is equal to, what did I, 50, that's 50. That's what I messed up here. There we go. 1/2 is equal to 25x squared. Divide by 25, that's going to give you 4 is equal to x squared, and x is equal to, square root both sides. X is equal to 2 meters. So there we go. There's the first one done. Second one, try to start figuring out what kind of energy you start with. So we start up high here, so that's going to give us gravitational energy. We do not have any kinetic energy because we're not moving. Doesn't appear to be a spring in this one at the beginning. At the end, the cart seems to be moving, so that is going to give it, yes, kinetic energy. It is at the bottom, so no gravitational energy, no spring involved, so no elastic energy. And again, we ignore the fact we don't utilize the internal here. Appears that probably the only thing we're going to put in the system is the cart there. So that's going to start us off with some gravitational energy here. Again, with the 4 bars. It says assuming that 10% of the energy is dissipated by friction. So we are losing some energy to friction. So I'm just going to put a little 1 bar of energy leaving. I'm going to label that 2 friction. And so that leaves me 3 bars of kinetic energy. So to write our equation, we got gravitational energy minus the work to friction is equal to the kinetic energy. Gravitational energy is mgh minus the work to friction. So it says that we lose 10% of our energy. So 10% would be 0.1, and it's 0.1 times by the initial energy, which would have been mgh, right? So it's however much energy we initially had, 10% of that we lose is equal to 1/2 mv squared for kinetic energy. So that's going to give us, we're going to kind of continue it on over here. Mass is 20 times 9.8 times by your height of 5 minus, we'll just have to scoot this over here a little bit, minus 0.1 times by all those same things, right? To find the 10% of the 0.1 is going to find 10% of the initial energy times by 1/2 times by 20 again times by v squared. So all right, there you go. There's that one. Moving on to number 3. So as we look at this, we started off here. We're going to start out with elastic energy. Looks like we got a spring compressed there. At the end, looks like we're going to have gravitational energy. Let's make sure we catch this, that the mass in kilograms is really 0.5 kilograms. You got to make sure you divide by 1,000 to change the grams into kilograms. So that's going to start us off with elastic energy. Sorry, I should have started right. In the system, as we think about the pieces of that we should include in the system, we would want to include the, what is a block? We want a block. And we would want to have the spring. Those are the two things we want to have in there. All right, so we start with elastic energy. And we pretty much, there's no energy added or subtracted. We end with gravitational energy, and that's all. So our equation for this one would just look like elastic energy plus 0, because no energy in or out, is equal to gravitational energy. So it's going to give you 1/2 kx squared is equal to mgh. So 1/2 times by 100 0.3 squared is equal to, what's the mass? 0.5 times by 9.8 times by h. H is what you're looking for there. So it's going to give you 4.5 on this side, 4.9 h. H is equal to 0.92 meters. Okay, cool. Moving on to the next one. So we got our bullet. Let's just catch that mass right before we get too far here. So the m is equal to 0.025 kilograms. Got to change that into kilograms. Let's see here. So we're going to start out with kinetic energy because it's moving fast there. At the end, right, no gravitational energy or elastic energy there. At the end, still no gravitational energy. It hasn't changed height. It doesn't have elastic energy because there's no spring. It doesn't have kinetic energy because it's not moving. So basically, we would have 0 energy, over on this other this other side here. So let's see here. What should we include in the system? Obviously, probably the bullet in the system. So, and then the question is, do we include the block or not? So if we kind of think about this, we start out with some kinetic energy. I'll go ahead and put four bars of kinetic energy there. We know that we have 0 energy at the end, so the only possibility is that all 4 of those bars of energy have left right there. And where did they go to? They went to the block. So we don't want to put the block in the system because, right, if the block was in the system, then I can't have energy out to the system, right? So I know that I have 0 energy at the end because I don't have kinetic, gravitational, or elastic energy. So that where did that energy go? I have to account for it. Well, the energy has been dissipated into the block. So I don't want to have the block in the system because I want it to leave and go to the block. So writing the equation, we've got kinetic energy minus the work is equal to 0. Kinetic energy is 1/2 mv squared. Work is force times by distance. You can look up that in the physics journal about work. You can see that that's one of the equations for work. And so basically continuing that on, going ahead and plugging in the numbers. X equals 0. We got 1/2 the mass, which is 0.025, times by the velocity, which is 350, minus the force, which is 500,000 or 50,000, sorry. Equals 0. And so now to go ahead and calculate that out, 0.5 times by 0.025 times by 350 squared. And this side gives me 1,531.25 minus 50,000 delta x. So add the 50,000 to the other side, then divide by 50,000. So 0.03 meters, which would be basically 3 centimeters. So there you go. There's that one. Lastly, the roller coaster one. So probably it's fairly good to draw yourself a picture for this one. It starts up high. This problem is actually very similar to the one in the kinetic energy physics journal example. So you can always look there. That might be helpful. But so we start out 75 meters tall. We end 45 meters tall. So as we think about the types of energy we have as the little cart goes through this whole little roller coaster, we're going to start out with kinetic or with gravitational energy because we're up high and we start at rest. At the very bottom, we're going to be going really fast, so that's going to give us kinetic energy. And at the end, you're going to have kinetic energy because you're moving and gravitational energy because you're up high. So you kind of have both. So there's not any energy lost. So let's see here. We'll put the roller coaster in the system. There's not really anything else to put in the system. That's kind of the only thing that you could put in the system. So let's see here. We know that we start out with all gravitational energy. So it does say with very low friction wheels. That just means that there isn't energy, lost throughout this whole thing. And also there's not energy gain. There's not anything that's adding energy as we go through this. So all of the gravitational energy will become kinetic energy in the middle one, right when it's at the bottom, and then the end it'll just have some kinetic and some gravitational energy at the end because it's got a little bit of both. As long as it adds up to 4 bars, then no big deal. It doesn't matter how many you do. So looking on to the right, looking at part B here, find the speed of the roller coaster at the bottom of the hill. So we can just kind of take a look at these first two here. So using these to set up the equation, the first two meaning the beginning and the bottom. So we know that we start out with gravitational energy. We know that we don't add or subtract any energy. And we know that at the end we have kinetic energy. So mgh is equal to 1/2 mv squared. So it's a 400 kilogram cart, 9.8 meters per second squared for G, and the H is 75. It's going to give us 1/2 times by 400. So then 400 times 9.8 times 75. So that's going to give us 294,000 joules of gravitational energy is equal to 200 v squared. So one thing that's kind of important to note is that the total energy that we have is 294,000 joules. So that means we have 294,000 joules of energy here, where it's all gravitational energy. We have 294,000 joules here of energy because, and in that case, it's all kinetic energy. And here, they all add together to give us 294,000. 294,000 joules of combined energy between the kinetic and gravitational energies. So just kind of pointing out that because we don't lose any energy, that's how much energy we have throughout this whole thing. So let's see here. You're going to divide by the 200. So square root both sides. That's going to give you 38 meters per second. And we're going to move along. Find its speed at the top of the second hill. So there's kind of, a couple different ways you could do this. You can set any of these equal to the last one. So like, for example, I could set the first one, the beginning, the EG, right, equal to the last one. Basically meaning where the gravitational energy comes from there, the kinetic energy comes from there, gravitational energy comes from there. So I could set it up that way if I wanted to, and that would work. So I could also set it up where instead of the EG, I could write EK, and that EK would be the kinetic energy from there. It doesn't really matter how I do it because, right, no matter what, I'll put back to the EG, right, I know that is, I don't even have to recalculate it. I know that it's 294,000 joules is equal to the kinetic energy of the cart plus the gravitational energy of the cart at the third situation at the top of the second hill there. So I got 294,000 because again, that's just the combined energy. That's the total amount of energy that I have. 1/2 times by 400 v squared. I'm looking for the v. Again, I got the 400. I got 9.8, and I'm going to put the 45 here because that's how tall it is at the second situation. So now to do some little last calculations here, we got 200 v squared plus, so we got 400 times 9.8 times 45. So that's going to give me 176,400. Subtract that to the other side, so 294,000 minus the 176,000. So that's going to give you 1,17600 is equal to 200 v squared. Divide by 200. It's going to give you 588 equals v squared. Square root both sides. And v is equal to square root of 588, 24.2 meters per second. There you go. So those are the answers to worksheet 7.4. Hopefully that makes sense. As always, let me know if you have any questions, and thank you for watching.